And boom.
Good morning, ladies and gentlemen. How many electrons must be gathered to make -1 coulomb of charge?
Okay, this is a definition here, and you have it in your notes. Can you find it in your notes?
Can you find it? -1 coulombs of charge. Now, let's go ahead.
Why don't you write it on the board?
Okay, the -1 part?
-1 coulomb of charge
So we got -1. How many electrons? -1 coulomb of charge.
equals,
-1 coulomb of charge equals, you want that 6 number?
then 1.60, well, no, 6.25
6.25.
times 10 to the 18 electrons.
Oh, there you go.
That's how many electrons have, and that is a huge number of electrons, and 1 coulomb is a huge amount of charge.
You might have seen us write it like this, right? It's the same thing, but I'm just putting the negative on this side. No? Oh, you're right. No, that's for the 1.6.
Yeah.
I apologize. You've seen us write it like this.
That's right. Okay.
So,
and we used this in the last unit.
yeah, we used in the last. So if we're talking about -1 coulomb of charge, we're talking about that many electrons.
That's
It's a lot of electrons.
Yes, it is.
Okay. What is the quantity of charge on 1 electron?
Now, boys and girls, you may have that memorized, but we can use this equation right here to calculate the charge on 1 electron.
All right, we're trying to figure out the charge. So that's the coulombs right here, and our answer's gonna go down here.
Yeah.
And what did we say? We said 1 electron is 6.25 times 10 to the 18th electrons, like that, right?
Yeah, and -1 coulombs is the charge.
Sorry, yep, -1 coulombs. So we just put this down here, put this up here. Let's go ahead and plug it into our calculator.
Make a
and get our
fraction out of
answer.
it.
Okay, so I've got -1 on top, and I divide it by 6.25 times 10 to the 18th, and I get -1.6 times 10 to the -19th.
You guys remember that should be a number should be familiar to you.
19th coulombs. These electrons cancel out.
Yep.
Okay. Now, if this was if I was asking for protons, it would just be a positive.
Positive,
number,
right?
right?
Because the charge on a proton is equal in magnitude. Yeah.
The saga continues. Okay. All right. If 25 electrons are rubbed from a shirt to a neutral balloon,
You just got through
which
doing
I just
that.
did, what quantity of charge is on the balloon? Okay, so 25 electrons?
Tell us
I can just
how much charge.
I can just put that right here, right?
You could, yes.
Or I could use this number right here.
Well,
I could
that's
do-
1 electron. So, yeah, you use it the official way here.
25 electrons in here, so I just do 25 divided by.
And that's basically going to be 25 times our answer.
So 25 divided by 6.25 times 10 to the 18th, and I get 4 times 10 to the -18th.
Coulombs.
Coulombs, yes. Okay, so now our answer
The
is
question is,
4 times 10 to the, what did I say, positive 18th? Oh, wait, did I put that
should be
right?
negative.
No, -18th. -18th coulombs right there.
And it should be -4. Because it's a
Oh,
negative
I forgot
charge.
to put,
No.
put my negative in there, yeah.
-4.
Yeah,
So-
25 times the -1.
And so that's how many electrons are now on our little twisted kidney balloon.
You little cute pie. So, and you said it's almost 4 times as much there. Okay. Oh, no, sorry. 25 times as much.
Yep.
Okay, what does each variable in Coulomb's law represent?
Do you remember the players? The players!
Gotta know the players play the game. Okay, so here is the electrical force.
Force électrique.
This is our electrical constant.
Yep.
K, 9 times 10 to the 9th Newton meters squared, so coulomb squared.
You got it.
And then this is the first charge we're talking about. That's the second
The quantity charge on one tank, quantity charge on the other tank.
And then this is just the distance between the two, and we square them, of
That's
course. Okay. Okay, so let's go ahead and do a problem. Go ahead and get started on this, people. I'm just gonna do this below here. Okay, so we're trying to find the electrical force here.
Yep, we just want to use Coulomb's law. This is a plug and a chug.
Woohoo! Plug and chug. My favorite in chemistry. Okay, So the first thing is just the constant, our electrical constant. Q1 is going to be, how many zeros? 1, 2, 3?
3, 0, and a 5.
1, 2,
And it's negative.
5, negative.
Coulomb.
Coulombs.
Coulomb.
And then a positive. 1, 2, 3, and then a 5.
Coulomb.
Coulombs. And then this is multiplication right here. Okay, and we're dividing it by 0.025.
Yep. Boys and girls, what'd you get?
What did you get? If you haven't done it yet, pause it. Okay, let's plug it in. Now, well, first of all, positive and negative, what is this going to be? Attraction or repulsion?
It's an excellent question.
No.
The opposites attract.
9 times 10 to the 9th times a negative 0.005 times a positive 0.005, and I divide that by 0.025 squared, and I get a negative, really big number, 3.6 times 10 to the negative 3.6 times 10 to the, let's see if I can count this. 1, 2, 3, 4, 5, 6, 7, 8. 8 newtons.
Yep.
Okay, so
Simple.
what did Mr. Boykin say earlier? He said this is attraction. Why is it attraction? Negative times a positive.
Opposites attract.
Or we get a negative answer. We know negative answer for attraction. Bada boom. Okay.
Bada bing, bada bang, bada boom.
And on to the next thing.
So now we're dealing with the field.
Yeah, so now let's talk about the field, the electric field. So we have our originating charge, which we represent by this, and our positive test charge. And in a little bit today, we're going to represent those two things using these. Okay, this will be our originating, this will be our test.
I like that.
An electric charge, our original charge, produces a field around it where forces are exerted.
Yep.
So this guy, there is an electric field around it, regardless of whether it wants to or not.
Yeah.
It always is. And the field lines, these are both examples of test charges here.
Yeah.
Okay.
Originating charges.
The originating charge. Now, what's going on with these field lines?
Well, they're going out, so
So they're going out, and so the zombie hand comes in and brings our test charge in, right?
Yeah. Uh-huh.
Okay. And we'll talk about the arrows in a second, but what happens to the magnitude of the test charge as I bring it closer?
Well, it's going to get more intense because the distance is getting smaller.
Yeah, exactly. So the closer it is, the greater the force.
Yeah.
Right? Now, if it's further away, it's not really feeling that force as much. Right? So it has less electrical force.
What about the
Going
direction of the force?
Well, this is always positive, right?
It's a test charge is always positive by definition.
So if I bring this in, okay, and this arrow, my zombie hand is coming in, is pointing out what kind of charge do we have here then?
Well, that's repulsion. They must be the same.
Okay. And repulsion, this is being this arrow essentially represents what's on here.
Yep.
Right. Okay. So this arrow is really pointing outward on my test charge.
Yeah.
Okay. Now how is this different over here? Okay. This is coming
It's
in.
being pulled in, so that's attraction.
Attraction.
Oh, it's cheating. It's telling you right there.
Oh, I see
Ah!
that. Okay. And so when it talks about these field lines going out, what that's really talking about is if you remember the zombie hand coming in,
Yeah.
how it had that arrow being drawn out like that.
That's right.
Okay, that's what's happening here. And the length of that arrow is determined by how close it is to our originating charge.
Yep.
Okay, I think we're done there. Practice
Well, I
problem.
think we went backwards. That's what we just did.
Oh, is it?
I think so. Yep. Somehow you got. Wait a minute. Hold up. Oh no, that's a different one. I'm so sorry, Miss Moore.
Oh, is it a different one? Are you sure?
Yeah. Uh-huh.
Oh no, it is right here. Yeah. it's
Okay,
different.
so everything's the same except you've got an originating charge, which is at 0.005 like
that's
we had before.
easy fix.
The only thing that's changed is the test charge is a very small one.
Okay, so I'm just gonna come over here now. So this is our electrical force, which we're trying to find.
Yeah.
Our K, our electrical constant, is the same.
It's the same.
This is our originating charge,
Yeah.
which I'm gonna leave.
Yeah.
And then over here, I'm gonna change this to tricky. Okay, 5 I know I was like, what? Times 10 to the negative ninth?
Yep.
So it's just a small.
And the distance is the
positive.
same. So it's the same situation we had before, but now we've got a test charge.
So let me just go ahead and
You can
find
hit the
my
cheat button.
my re-entry button here.
It's a shift enter.
Yeah, so you guys see it in here? Okay, so I'm just gonna. Okay, so 5.
Are you gonna
Times
have to do some inserting? Will?
10, yeah, probably to the negative, and then I insert the negative ninth. That look good? 5 times
I can't
10.
see it.
Yeah, there we go. I think we're good here. Okay.
And
And we
divide
get-
by 0.025 squared.
We get negative 360.
Negative 360.
Negative
Oh,
360.
oh yeah. See, we kept the numbers the same. We just kept the magnitude of the number.
Ah.
360 newtons.
Yeah, because before it was just, this is a lot smaller.
That's a lot smaller.
Okay.
Before it was 5 times 10 to the negative 3. Now it's 5 times 10 to the negative 9.
Okay, so that's how many newtons of electrical force are going to be exerted on that test charge as it moves through that electrical field.
Yeah. Well, at that particular point in
At
the
the-
field.
Yeah, at that point in the field. See, oh yeah, at that point right there. It's really close. Okay. All right. So the intensity of the field depends on the size of the originating charge and the distance from it.
Yep.
Do you guys remember the light bulb thing we did the other day?
Oh yeah.
Right, so we just had the light bulb, which was really bright, and we had imagine that piece of tape on it like that, you know, and it was really, really, really intense. And then we put the smaller globe over it, and that had again that little square, and it wasn't as bright. And then we put the big globe on top, which is a lot further out, and it still had that same size on it, and it was a lot dimmer.
Yep.
Right, and so that's what we're talking about intensity. So the further away you get from it, the less intense it's going to be. But it also depends on the size of our originating, like the intensity, the magnitude.
Yeah, if you have a small charge or like the big Van de Graaff generator back here, which
Yeah.
has got a plastic thing on it, you can have a lot of charge.
It looks like a jellyfish. Okay. So the electrical field just is.
It
So,
exists.
Yeah. So whether it wants to or not, it is. There is an electrical field around our originating charge.
Yep.
Okay. A test charge, this guy, or with our zombie hand coming in, just measures the presence of the electrical field in space.
Yep.
It's doing us a service. Okay. Okay, here we go. So the ratio of the force on the test charge, on the test charge,
So yeah, the ratio of the force on the test charge to the quantity of charge on the test
Oh,
charge.
thank you, defines the E.
Yeah.
Okay. And E is our electric field here.
Yeah.
So we've got the force, we know our test charge, we can figure out what the electric field is. Coulomb's law predicts the force between the originating charge and the test charge.
So basically, it's the same Coulomb's law we've been playing with. We're just making it specific now for our use with a particular originating charge and a test charge.
So I think that's it for our slides here. What you guys are going to be doing for homework is, so we have this Lost in Space. It's going to be attached here. You're just going to do page 1. There is 2 pages. Don't do the second page yet. Hang tight, okay? Just do our first page here. All the way to you're going to finish up number 4.
Okay. Boom.